Hello, everyone, and thank you for joining us today. I'm Sean Fensky, Editor-in-Chief of Medical Product Outsourcing and moderator for today's program. You've logged on to the MPO webinar, What Every Engineer Should Know to Prevent Warp. Before we get started, I have some housekeeping announcements. For those of you who are interested in revisiting the information you hear today, or if you'd like to forward it to a colleague, once the webinar is ended, this session will be archived for a year. The archive will be able to be accessed through the MPO website, which is at mpomag.com. Also, we will be accepting questions throughout the presentation. You can type your question into the box provided in the webcast window. We will collect all questions and hold them until the end, but please feel free to type in questions as you have them. To enhance your viewing experience today, feel free to customize your window display. You can move the windows around by clicking on the top header space of each window and dragging them with your mouse. Also, you can activate the closed caption option by clicking on the CC button in your media player. Finally, share your reactions to the content being presented today with the emojis provided. Your feedback will be seen by today's speakers. And now, before I introduce today's speakers, I'd like to take this opportunity to thank our sponsor, Aptex. Aptex represents the aptitude and excellence of more than a dozen companies with a 70-year-plus track record in manufacturing, helping medtech customers solve tough challenges with confidence. The company helps teams bring complex components and devices from idea to market success with entrepreneurial speed and sustainable results. Now let's get started. Today we're joined by two members of the Aptex team, Beth Harrison-Meyer, Senior Vice President of Global Marketing, and Ray Scherer, Global Engineering Manager. Beth brings more than 25 years of strategic marketing leadership in diverse environments, ranging from the Fortune 50 to startups. She is known for building brands and launching disruptive products and programs. Beth was instrumental in the rebrand to Aptex in 2023. With more than 30 years of expertise in DFM, tooling, and molding, Ray is a predictive engineering wizard who helps customers avoid costly missteps and optimize their designs for success. From the first spark of an idea to full-scale production, he ensures every part exceeds expectations. Now we'll begin with today's presentation. Beth?
Thanks, Sean. We're going to start with a brief video.
In the bustling city of MedTechtropolis, where speed, quality, and life-saving innovation reigns, an Aptex engineer named Ray Scherer discovered his extraordinary gift for predictive engineering. With an uncanny ability to foresee and course-correct using design for manufacturing, giving him an ability to dodge delays and evade catastrophic costs, he became known as the Great Raydini. As medical device and manufacturers faced surging demand for their groundbreaking products, a sinister force loomed on the horizon. Warp, a rogue villain with the power to manipulate time and space itself, emerged from the shadows. Driven by a thirst for chaos and destruction, Warp sought to disrupt manufacturing operations and plunge profits into darkness. The Great Raydini, armed with predictive prowess, rallied the Aptex engineering team to defend against Warp's temporal terrors. With the fabric of reality bending to Warp's will, they faced a relentless onslaught of twisted challenges and warped components. Determined to save their city from destruction, the Great Raydini, his team, and fellow Avenger Brian Pelly pushed themselves to the limits, using their ingenuity, resourcefulness, and combined mastery of Moldflow to outsmart Warp at every turn. After a grueling battle, the Great Raydini, Brian, and their team emerged victorious, banishing Warp back to the depths of the time-space continuum. With MedTechtropolis safe once more, the Great Raydini's legend grew even stronger, inspiring engineers everywhere to harness the power of technology for good.
So I hope you enjoyed that video. We love what we do, and we like to have some fun with it. So what we're going to cover today is I will do a brief intro into Aptex and then turn it over to Ray for the heart of the presentation, or rather the Great Raydini. He will cover tolerance planning and the impact of shrink and shape control and how to manipulate warp. And then, as Sean said, Q&A at the end. So while aptics is a new or newish name, our experience is not new. As Sean mentioned, we bring together the aptitude and excellence of more than a dozen companies with a 70-year track record in complex design and manufacturing. We do this across a global network of more than 10 locations with a broad range of capabilities. But what makes aptics aptics is our team of experts, and our make it happen mindset. We like to say that engineering is the heartbeat of the company. Our team loves nothing more than diving in, partnering with customers, and solving complex challenges. And you'll see some of that today. We do have a very broad set of capabilities, and we work from D&D to finished device assembly. Of course, we're talking about injection molding today, but we were a pioneer in dip molding nearly 60 years ago, and also have decades in blow molding, as well as a range of extrusion and coating solutions, supporting components, sub-assemblies, and finished devices in a breadth of complex clinical markets. Our history in molding dates back 70 years. We have press sizes ranging from 5 to 940 tons, so supporting small to large parts. But where we shine is with complex products and materials. With materials, we work with hundreds, but in particular specialize with high temp and highly engineered materials, as well as filled resins. Today, you'll hear and see a lot about how we handle DFM and predictive engineering and Moldflow. It truly is best in class. The great Raydini has that name for a reason. And then another key area where we are very strong in supporting customers is validations. We're able to do this in a very streamlined manner using scientific molding, design of experiments, and a CT scanner, and actually have a new CT scanner coming in the next month. So Ray may not be an actual superhero, but he does save the day quite often. And he comes by the nickname Raydini very organically. Like Houdini, Ray can work his way out of any challenge and partner with our customers and really save the day within MedTech. And I am very pleased to turn this over now to Ray.
Well, thank you, Beth. Well, I think I got to start off with a disclaimer, and that is I take no responsibility for what people call me. I've heard a lot of names over the years, so thank you, Beth.
You're too modest.
So I just wanted to maybe give you guys a little bit of background. If you're tuned into this topic today, we probably have a lot in common. For me, I started some 30 plus years ago in this industry in molding, and honestly, showing up at a molding plant and out on a molding machine was like going to Disneyland for me. I really enjoyed it. What I quickly learned, though, in my early days is when I would sit out there at the press and all excited about taking those first shots off the mold and getting them in my hand, I would look at them, and oftentimes I would say, why does it look like this? And that was the crux of the whole issue for me. Is I didn't like surprises at that point in time. I mean, I enjoyed surprises for birthdays, but I didn't enjoy them for manufacturing. So it kind of set me off on an approach. It's like, well, how could I predict events before they happen? And if I could predict them, then maybe I could steer around them. So I had a couple. There's a lot I could share with you, but today there's a couple of topics that Beth spoke about that I wanted to share with you, and hopefully they prove to be helpful to you as well. They're really just lessons learned over time for me. Let me kind of get into it. So what I'll talk about is the DFX, and really, as I mentioned, what I needed in my life was a way to predict and answer one primary question: what might happen? Now, it's a big question because there's a lot of things that can happen. So I broke it down into pieces and started to pursue what I call the predictive DFM, DFA approach. And I just wanted to kind of walk through these with you really quickly. Phase one, I identified as predicting tolerance outcomes. I don't know how many of you out there have experienced, parts that may look good, but then you put some metrology to them and you find out, well, I'm out of print. So the big question became, how could I predict that, or at least know concerns ahead of time? If I did know them ahead of time, I might be able to do something in a mold to at least be steel safe and counteract it. So we'll talk about that a little bit today. The next phase was predicting shape and moldability outcomes. So many times I would get a part in my hand after molding, and you look at the part, especially larger parts, it'll show up even more. I would end up with warp, and it would be so much warp that it was something I never expected. And so at that point, you got an expensive mold and you're trying to scramble to figure out how you can fix it. Customer's not really happy with it. So I needed to spend time, see if I could figure that out. The idea was if I could predict it through certain tools, then maybe I could course correct before we ever got to that stage. The next area was this phase 3, which is predicting assembly challenges. I mean, most of these parts go together in assembly. And so oftentimes we would have parts that were great, but by the time you start putting together with other units, you notice things, So we had to develop a way or a method of going in and analyzing fits. And it really starts with a partnership with customers and understanding how they're being used, so that we can make proper decisions related to assembly. So phase 4 was predicting tool reliability. I often say, as a contract manufacturer, we make our money in pennies, but we can lose it in dollars. As you guys know, molds are very expensive. And for us, they need to be extremely reliable. One thing I never really liked doing was taking a customer's part design, throwing it over the fence to a tool shop and just have them build a mold. While they're experts at building tooling, they're not always experts at processing side, and the two have to come together. So we would spend a lot of time kind of involved with the details of molds, because we really need to put them in a press and know they're gonna last and gonna run for us, and that impacts the customer as well. Predicting metrology challenges. This is another one we won't really get into today, but it's a common one. I've seen programs, where it may take 12, 16 weeks to build a mold, but you could spend a whole lot more time rummaging through all the metrology and trying to understand it and make sure your part meets print. A lot of issues in there, especially with plastic, since plastic doesn't shrink uniformly. We'll talk about that today. It's sometimes very challenging to hit your numbers, and you could have datum structures that don't align well with warp and so on. So there's a lot buried in this topic. So we spend a lot of time trying to unravel that, because that's really where we can pick up time. Also wanted to be able to predict the molding process. So often we would go out in the early days and have to investigate all of our parameters on the machine, spend a lot of time, spend a lot of money, experimenting, running DOEs, which are still great tools. But I realized that there's other tools in place. Beth mentioned Moldflow. We live in that package, and we're able to actually optimize processes through simulation before we ever reach the floor. And we found that to be very, very good at getting us those initial conditions to start with, where you can see a lot of results that you don't necessarily pick up with the eye on the floor. So that's been a great tool. Lastly is developing a good, robust validation strategy. Oftentimes this is sort of overlooked, but we try to team up with our customers very closely to come up with a strategy that wrings the risk out of the program, but doesn't go overboard, but also doesn't come up short. And a lot of times, this discussion, it can be overlooked, but it's something that we try to spend time on and really make sure we worked out an ironclad approach. What we'll cover today, Beth mentioned, we'll talk about tolerance planning and how to understand the impact of shrink variation on tolerances. So there's a little trick in there I want to teach you guys that's been useful for me and hopefully useful for you. In the second phase, we'll talk about shape control. And this is where we'll go over some shrink principles and teach them to you so you can put them in yourself into control of your own work. They're lessons learned over time, but but very impactful. All right, let's get into it. So this first phase, we're going to talk a little bit about shrinkage. What is shrinkage? In a mold, we often think of it as a linear rate. Many of you have heard that with tool makers. What's the shrink rate you want to use? And the shrink rate is often determined from the manufacturer on a data sheet. Like in the panel over here on the right, I have a Macrolon 2458, just a little clipping out of their data sheet. And it shows some shrinkage rates over here in the table. You can see the one at the bottom is sort of a range of 0.5 to 0.7. Data sheets often express it in percentage, which is what they're doing here. And then you'll see there's a couple other rates in green that I have noticed there and noted. We'll talk more about that. Tool makers often express it in inches per inch. They could say 6/1000ths per inch, but it's really a scale factor of 0.6%. And that's what they'll scale up in their mold if they're doing polycarb, for instance, to build the tool, in hopes that when it shrinks, it'll hit size. All of those values will use to scale the mold, as I mentioned. So now there's another way to express shrink that I want to bring up. So as I mentioned earlier, if you're familiar with Moldflow, we use it a lot. Moldflow expresses shrink a little differently, and this is a key to what we'll talk about today. Moldflow expresses that volumetric shrinkage, and it's basically the difference between melt temperature volume and solidified volume. So if you think about it a minute, when you heat up a plastic, it expands, density drops. When it cools down, it contracts and becomes more dense. That delta between the melt temperature and the solidified volume is really what Moldflow calls volumetric shrinkage. And here's a little pictorial example on the panel on the right. You can see the little white cube represents the melt volume where it expands. And then as it cools down, the little purple box is the solidified volume afterwards. And that percentage change in that overall volume is what Moldflow will report. If you look down on the left side, down the lower pane there where I have the Moldflow Macrolon 2458, you'll see the densities. This is out of Moldflow. The normal solid density for polycarb is 1.18, but when you heat it up, you lose the density, 1.03. And there lies some of the challenges that we have in plastics. Important note to make here is that volumetric shrinkage is not the same as linear shrinkage, although they're proportionally related. So if you look over here again on the right-hand panel, this is a clipping out of Moldflow for some shrink study work that was done with Macrolon 2458, a polycarbonate. And you can see in green where I've kind of highlighted that row, it shows a couple of different rates, the parallel shrinkage and the perpendicular shrinkage, which is cross flow. And again, we'll talk about that a little bit more here later in the presentation. But you can see 0.7%, 0.8%. But then you look on the far right, we got volumetric shrinkage is at 2.45%. That's how much volume we would reduce. So while they're related, they are different numbers. It's important to point out. There's a couple of forms of shrinkage that we need to address. One of them is isotropic shrink, and many of you might be familiar with that, but really it's just a fancy way of saying that the shrink in the flow direction and the cross flow direction is very uniform, virtually the same, and we'll call that isotropic. In contrast, there's anisotropic, which is different in the two different directions. So in the bottom image I just put up there, you'll see the flow direction. But in that flow direction, the shrink rate will not be the same as the shrink rate across the flow. And therein lies issues that will create warp. And what we can do to battle that is what we'll talk about a little later in the presentation. So another important thing for everybody to keep in mind when they're picking resins is that there's two primary families, and many of you might be all aware of this already. There's the amorphous family of resins, and in their molecular alignment, they're very random in nature. And what that does, random and disordered, you can kind of see the panel on the right. and they're very isotropic. So because it's so random, you get a fairly uniform shrink with amorphous resins in both the flow and the cross flow. In contrast, you got semi-crystalline resins, which are very regular and ordered inside the part. And that order causes deltas in shrink between cross flow and flow, which is, we'll call it anisotropic. And so good thing to remember, because as you get into designing parts, depending on what you're trying to achieve, one of these families might be better than the other. A further complication, which we won't get into today, is filled resins. So the moment you introduce fiber into these resins, the anisotropic behavior gets worse. And it really has to do with that fiber aspect ratio, how long the fiber is compared to its diameter. I like to think of it this way. This is a picture in my head. You can picture it as logs in a river. The river is flowing just like plastic flows. Those logs, which represent glass fibers, I guess in this particular case, they could stack up on each other. So end to end, they can get very close together. But across them, there's plastic in between, or water, as we see here. So as that polymer begins to cool, the shrink across the logs actually gets higher than the shrink along the length, because the logs are holding it back from shrinking. And so you end up with a much lower shrink rate in the flow direction, and then a much higher in the cross flow direction. But again, today we'll focus more on unfilled resins. So good question is what kind of rates can we expect? And generally speaking, amorphous resins will shrink about 0.4 to 0.8%, pretty common. In the chart on the right there, I just threw out some common amorphous resins. You got polycarb, ABS, polystyrene. You got the Ultems, the PM, the acrylics, PS, the polysulfones. Those are all amorphous resins, and they all tend to fall in this 0.4 to 0.6, or if you're talking to a tool maker, 4 to 8 thousandths per inch. In contrast, when you go to the semi-crystalline resins, it cranks it up quite a bit. You'll commonly see 1.4 to 2.2%. Those are resins that you see over the chart. Typical ones are polypro, polyethylene, acetals, your nylons, PBT, PPS. Those are all semi-crystalline resins that hover around these higher shrink rates. So if you notice, these rates can be up to 3 times different, which is important for the conversation today. So take-home point is amorphous resins are dimensionally more stable, something to keep in mind. There's other reasons for picking different resins, chemical resistance and so on, but generally from a dimensional standpoint, amorphous resins are going to deliver a more dimensionally sound part. Shrink can vary for many reasons. This is what we want to talk about today. Part thickness, and I'm sure many of you are aware of that. Part thickness, as it increases, so if you have a 60 thou wall versus a 150 thou wall, that wall thickness will have influence on shrink. As it gets thicker, you will get more shrink out of that wall. Pressure also has an effect. As pressure goes up, you can pack out the density harder, you're going to shrink less. A good little pictorial is the picture I just put up there. This is just a flat little plate with a gate cone up the top, injecting plastic from the top and flowing downward. You can't really see the numbers probably too well, but at this particular one, we have about 7,600 PSI of pressure up north, and then it gets down to 0 at the bottom. That delta across there, that causes the lower end to shrink more than the upper end, and we'll see that. Related to it is flow length, really. So the next slide I put up is flow length, and this is a volumetric shrinkage slide that I have up, or picture I have up, and it varies. So we're getting still at the top, and you can see that the volumetric shrinks up around 2%, 2.2. By the time it reaches the end of fill, down at the bottom, you're at 3.5. And so flow length matters. As flow length increases, like distance away from gate, you can expect shrink to go higher. And here's another really important one. Cooling rates can affect shrink. So the faster you can cool an area, the less shrink you might see out of that particular area. And we'll talk about that. So the important take-home point is volumetric shrinkage varies throughout a part, and that's on every part everywhere. Even though you design with a uniform wall, you can end up with variable shrink throughout the part for these other reasons: thickness, pressure, flow length. So when they do vary, shape will vary. So this is where the struggle becomes. You know, you got your nice CAD file, you want your part to look like the CAD file, but you pull it out of the mold and now it doesn't. So here's a little magnified shrink or warp picture of these two plaques on the left. This is multiplied 30 times, but you can see the effects. It's sort of trapezoidal in nature. It gets narrower as it gets towards the bottom, it's larger as it is towards the top. And that's the principle behind it. So the question is, how can we manage risk? Well, there's some ways. I mean, one we've talked about, start with an appropriate resin. So if you've got a very, very sensitive tolerances, tight tolerances that you need to drive, you know, consider amorphous resins over semi-crystalline, good place to start. And be real about your tolerances. It's so easy to take a model as a designer and bring it into a drawing and just tolerance everything at ±1. And the truth is, if it came out that way, you know your part would work just fine. The reality of it is it puts handcuffs on the manufacturing side, because you will get variation happening. So one way to go, you know, that kind of accelerate speed to market as a designer is just to be real about your tolerances and really put numbers on there that make sense. Use sound reasoning, tolerance stacks, whatever you need to arrive at your numbers, but always start large and work towards tight. Don't start with tight and work towards large. That'd be my suggestion. But whatever you end up with, there's a way for you as a designer to gauge how much risk you've put into your design. And this is what I want to show you. So the question is how tight is too tight when I put a tolerance on a number, on a dimension? So this is a little equation I want to teach you. So if you take the one-sided tolerance of a dimension, so for instance, plus or minus 10, if you take the 10 and divide it by the feature nominal, you'll get a number. And that resultant value indicates how much shrink error your tolerance can accept. And I'll explain that more. So here's the equation. One-sided tolerance divided by the feature nominal equals the tolerable shrink error. And if you look at the chart over on the right, I calculated some. So in the column on the left is just a size, a nominal. And I got some tolerances across the top. If you just take that 60 thou thickness and a 1,000th tolerance and you divide it, you come up with 0.0167. So basically, from a shrink standpoint, that's saying I could be off as much as 16 7/10 per inch, and I'd still be in print at this 1,000th. In contrast, if you go down and look at the 1-inch dimension, if I take the 1,000th divided by 10, I only got 1,000th of room. So if I miss my shrink rate by 1,000th, I'm going to be out of print on this. So let me show you how this plays out. So what I typically do to try to get a handle on it is I'll look up the shrink rate for the resin. So let's say it's polycarbonate, and I just use a margin of about 25%. And I say, okay, I'm pretty confident that this whole part is going to be within plus or minus 25% of nominal shrink rate. So I'll do a calculation. So I'll call it my error interval. So I'll take the 6,000th shrink rate multiplied by 25%, and I'll say I'm 100% confident, or let's say 99% confident, that that whole part is probably going to be within plus or minus 1.5 of my 6, with all that variation we talked about. So it's really saying my confidence range is a shrink rate of 4.5 to 7.5. So you say, well, what do you do with that? Well, if you go ahead and do your shrink error, the calculation I just showed you, if your value is greater than the 1.5, you're at a low risk. That means your error available to you is much higher than the shrink, and are in the interval of error that we're expecting, and you're low risk. In contrast, if you do the calculation and your error value is higher than 1.5, you're at high risk. Well, here's a little chart over here on the right. The red is all high risk. This is based on a 1.5 thousandths error bar for polycarb. You can see that all the reds are below 1.5. So those are dimensions that I wouldn't expect to hit out of the gate, or could be at high risk. Typically what I would do is then look at a steel safe strategy around those. If they're in the green, you're pretty safe. If you're in the yellow, well, you need to look at that and make a decision. So this is a method that we employ in order to determine what dimensions could be at risk, and then try to employ a steel safe strategy, which is what I mentioned down here. So what we do is I have a little tool, a little spreadsheet that we put together that automatically calculates like this. So we'll take a customer's drawing, we'll populate it with all the numbers. We'll put an error bar in up here on the upper right. You can see it. We put the expected shrink rate, we put the error bar in there, and it kind of flags which ones could be a concern. And then we'll take a look at those and decide how we want to approach it. But it's a good little tool for you guys to use if you're a designer, to get some idea on how much risk you're putting into it via tolerance. Now, a lot of times these tolerances are real, and that's where you need to be. And then you just have to work with the molder to come up with a plan to to groom the mold into those tolerances. Okay, shape control. So here's where we're going to take these principles and apply them to shape, which is really the center of the discussion today. And the question is, can I use the shrink to my advantage? And the answer is absolutely. You can use it to manipulate warp. It took me a long time in my career to really realize this. I knew if I could predict it, then there was something going on there that I could possibly control. And that was big for me when I finally saw this play out. But let me go over just some really basic principles that feed into this discussion. So on the shrink side, we know from our earlier discussion that resin within a part does not shrink uniformly. And that's the case with all parts. So going into it, one rate's not going to solve it all. If this principle number 2 is important, if your volumetric shrinkage patterns are balanced about a neutral plane passing through the center of mass, a part will not warp. Let me explain that for a moment. So we talked about volumetric shrinkage. We talked about it varying all the way through a part. If that variation is redistributed, or is distributed in a way that it's very balanced about a plane. If you look in the image I have here, I kind of drew a cross section and I drew a line through it indicating a neutral axis or neutral plane in this one axis. If you got equivalent shrinkage on both sides, the tug of war will balance out and the part will be flat. If you don't, then the part will warp. So the important point here is that you need to strive for balanced volumetric shrinkage if you want to achieve optimal flatness. Now, not every part has an optimal flatness requirement, but a lot of them do. And this is where, if you understand this principle, you can apply it and actually attack that. So this principle here, this third one I want to bring up, is probably the biggest eye-opener for me. And I would say if you go away today not remembering anything I went over, if you could remember this one point, it'll be huge for you, huge. And that is shrink decreases along edges. So very simply, I have this little plate over here on the right. Let's just take a look at it for a moment. There's a legend. Blue is low volumetric shrinkage. Red is high volumetric shrinkage. And you'll see all the color banding going on. So if you look closely, let's walk down the middle of the part. The gate's in the middle in this case. That's what that little cone is. As you start to walk away through the middle, you'll see some values. Hopefully you could read them, but it's about 2.5% is that first one. And then it goes up to 3.7, up to 4.1 on this particular run. So that's that distance from gate phenomena we talked about. It's that pressure drop phenomena. So we're actually shrinking a whole lot more at the end of fill than we are close to fill. Makes sense. But now look at the edge. It follows the same pattern. In other words, right in the middle, it's about 1.4%. And then as you walk down, it goes 1.7 to 2.2, 2.6. So it does increase as it goes, but from a magnitude standpoint, it's far less than the middle. And this is the part that I didn't understand for the longest time. But it's one of the major drivers of warp. So again, if you remember nothing else, remember this picture in your head that shrink decreases along edges. So I want to show you it played out. What we have here is volumetric shrinkage over some varying lengths here. So this is this simple little part. It's a plate with a couple of ribs. You can kind of see the picture. First note I want to make here is that the part surfaces with higher shrinkage may be shorter than planned. So if you look at this legend again, you could see that blue is low shrink, red is high shrink. And we have anywhere we have multiple colors kind of going through this. You can see the green. So anywhere where you see a green, it's going to be a higher shrinkage. The part is going to proportionally shrink more than in the blue regions. So the opposite is true. The lower shrinkage occurs it becomes longer. So anywhere you see the blue, you're going to be proportionally longer when you come out of the mold. So your mold is proportionally cut, but when that part comes out, you're going to have a long length of blue and a short length of green, and it's going to cause some distortion. So if you look down to the middle view, I tossed in a neutral plane, that red line, you can see it. And if you look north and south of that line, you start to get a little bit of a picture. You look to the north, you see a lot of blue in those ribs, especially concentrated in the center. When you go to the south, there is some blue, but it's only along the edges. So we have this imbalance. You can kind of see it better in the perspective view up top. You have a lot of blue up top. So something's going to happen because all that blue wants to go long, all that green wants to go short. And the picture down below, which is magnified, I think it's 10x, visually, you can see what happens. It curves. The top surface that's blue goes long, the green goes short, and that part turns into a cylinder and bends. And once I realized that, I figured, okay, now I think I got a way to attack this and maybe fix it. And that's what we want to show you here. So again, every part contains elements of both of these shrinkage, and you can see it clearly in this particular slide. Okay. So next up, I wanted to take and apply these across a bunch of different shapes. So we took the flat plate, upper left corner. We'll show how that comes out. We'll take that flat plate, we'll add two little ribs, and that's really what you just saw. And we'll compare that. Going to the middle views, we will take the flat plate and we'll add, well, it's still the same two ribs on the south side, but we'll add a couple of ribs to the north, but we'll only make them half height. And we'll, the question is what will that do for us? We'll also take that same plate to the south, there, the one on the bottom, and we'll make ribs equal height. And we'll take a look and see what that does. By now, you probably already have in your mind what these things are going to do, but we'll take a look together. On the right is a little different technique. I mean, you might say, hey, Ray, this is all fine and dandy that you're doing all this, but I can't have ribs on the outside of my surface. And I'd say, okay, that's okay too. There's different techniques we can apply. And this one here, I said, okay, no rib on the outside. Let's put some grooves in there. And let's apply that principle that we learned earlier, that thickness affects shrink. So if I get thinner, I should have a lower shrink rate. And if I could create some bands of lower shrink rate on one end of the plane to offset on the other, maybe that would do something. So let's take a look and see what happens. So here's our flat plate. And this is a cross section of volumetric shrink. You can see in the middle, it's highly green. Around the edges, it's blue, very uniform all the way around. So if you drew a plane through the middle of that, you can see that's fairly uniform volumetric shrink, and you might expect it to be flat. And here it is. This is, you can see the ghost lines where the part started, it shrunk back, and we're basically very flat still, no issue. We go to the next one, which is the one we've already saw, which is the two ribs down below. But you can see through the cross section that we got a lot more blue to the south on top of those ribs, but very little to the north side. So what does that do? In this case, it creates a smiley face. It's just inverted or flipped around from the previous slide that we looked at. So now let's make some changes. So now we'll go in, take this flat plate, we'll add those two little short height ribs to the north. They're half the height of the ones on the underside. And if you look at the cross section, you'll see there's still more blue to the south than there is to the top, but there's still more to the top than there was before. So maybe this should help. Let's find out. And sure enough, it does. If you look at the shape, it's still smiling at us, but it's not quite as much as it was previously. So the question is what if we make those ribs full height, so we're completely symmetrical? If you look at the cross section again, you'll see the blues all pretty much match up symmetrically. And what might we expect is this, it'll stay flat. So it'll shrink, but it'll stay nice and flat. Lastly, the groove idea. So we threw some grooves in. We still have all the blue that we'll have down at the bottom of the rib. But now we've introduced a couple of bands of blue at the base of the rib just by virtue of these little slots that we're running down. So let's see if that balance can help us. And let me click ahead here. And there you go. So again, at 10 to 1, what's going on here? Okay, at 10 to 1, it's very, very flat. Very, very flat. And so you see a little bit of a smile. So it didn't completely get it out, but it got it a whole lot flatter than it did. This next one I want to show you is employing these concepts on something a little more complex in geometry. This is a laparoscopic handle. It's a very curved one, and as a designer, we would normally design these things with a 80 thou, a uniform wall, and that's how this one was designed. It's a 2mm wall, very uniform. If you look at the pictures on the right, again, this is volumetric shrinkage. You can see the legend across the top, blue to red. And if you look at the outside of the part, I put some examine points there. You can see it's ranging in the 4% range across the top of the part, volumetrically. Along the ribs, you're at 5%. If you flip it over and start to take a look, you can still click on the main walls and see the 4% along the center, but along the edges, you're in the 2s. So here's that edge principle we were talking about, that's shrinking less than the center. So that long length is going to have to go somewhere, and that center is going to have to shrink more. So it kind of gives you a hint which way this is going to go. For this particular example, all we did was focus on the handle. We didn't do anything with the head of the part. So let me see what that looks like. 10 to 1, there's your smiley face. So it took the part, and as predicted, it warped upward, gave us a smile. So the question is, what can you do about something complex like this? I don't want to put ribs to the outside. Can't do that. So here's a little trick I learned that is very effective, especially for clamshell handles. So we took this handle, in that blue area, we decided to do some modification to. So the question is we're starting off at 80. What if we slowly thin it down, and let's do a very extreme case, and I went all the way down to 45 thousandths at the top. Now that's getting thin, probably too thin than you'd ever want, but for illustration purposes, we went there. So we went from thick to thin in the middle, back to thick again at the edge. So in contrast, change number 2, we did a little less. We did still started with the 80 thousandths and then tapered it down to about 60, and a little bit less. That's something probably more reasonable. And let's see what this does to our shape. This is the baseline we talked about earlier, just looking at shrinkage at the top. There's all your 4s and 5s. The next one is where we thinned it down to 45 thousandths. Look what happens. that top band where we're getting thin changes drastically. We went from 4s all the way down into 1%. So something's going to happen here. On the next one, where we didn't go quite as deep, we still brought it down. We got down into the 2% range, which, if you remember, is very close to the range we're seeing on the edge of the part. So now we're starting to get some balance. Let's see how these shapes look. So again, the constant wall version, which you saw earlier, is this pretty aggressive smiling face. On our first change, we went down to 45. Look what happens. It actually flips the other way. I kind of call this the holy grail. When we hit this point, we're actually able to manipulate shape to tune our flatness. And this is huge because it's actually steel safe in a mold. And so obviously you don't want to frown either, like it's showing. Let's go to that 60 thou one and see what it looks like. And it comes in fairly flat. Again, on the right, we haven't addressed any of that. We only worked on the left. And you can see we're starting to approach flat. Now we could tune this more and try to get it really flat, but it is a technique. It's a great technique to employ when you're creating handles for any kind of laparoscopic handle or any kind of surgical device to be able to control flatness. So kind of just a quick summary here of what we learned. I know we went over things pretty quickly, not a lot of time, but let's just review. Amorphous resins are dimensionally more stable than semi-crystalline resins. And that's very important for you guys to think about as you're picking resins, and give that a lot of thought. It'll help you, be victorious. Linear shrink rates aren't the same as volumetric shrink rates. We talked about that. So just because a tool maker's putting 0.006 inch, per inch shrinkage into your mold doesn't necessarily mean that's what you're going to see. You can tolerance-related shrink risk can be identified using that simple calculation that I showed you. So it's a good way for you to assess what you're up against. And then, of course, lastly, balancing the volumetric shrinkage about a neutral plane or neutral axis is essential for shape control. So these are some important points that you could incorporate when you guys are thinking about your designs and designing new products. So that's pretty much, Beth, my presentation. Let me hand it over to you.
Thanks, Ray. I learn something new every time, but definitely not a mold designer or molding expert. But you are, and I think as everyone watching can clearly see, you love diving into solutions and you love collaborating, and that's what we're all about. And we love to get your questions, get your challenges, and we'll take them now or at any time in the future.
Fantastic. Well, thank you, Ray, for that thorough and informative presentation. Once again, don't forget this webinar will be archived on mpomag.com for a year. Now it's time, as Beth indicated, for the question and answer session. We'll try to get to as many questions as we can. The first question for you, Ray, is, do you think the SPI 1998 standards are applicable for tolerances of a given resin, or is that obsolete in modern times?
Yeah, no, that's a great question. I've looked at those charts, and they were definitely born out of these principles that we talked about today. And basically that standard points to length of dimensions, and as you get longer and longer, you have to gather more tolerance to be in print. And that it's certainly the concept is still true today. The reality of it is we see our customers pushing the limits of that. I mean, they need tight tolerances, and so really what you have to plan on when you're getting outside of those limits is you have to look at strategies to tune steel into a process. So it's really important. You have different aspects of this happening. I mean, for instance, you do have variation of lot to lot. That's somewhat controllable, but you will get some lot to lot variation, which will always be there. But you have the initial shrink variation too. So you can get around that by tuning your steel into a process and locking it in and achieve better results. But the principles behind that are still the same. Your tolerances as you get further will impact it more, and that's what you'll see in that little equation I taught you. If you apply that, you'll see it play out.
Great. The next question we have: what is the practical value of volumetric shrink rate? Volume change can be hard to measure.
Yeah, it is. It is. I mean, it's really practical in Moldflow. I mean, if you hold a part in your hand and you try to understand volumetric shrinkage with it, you're not going to get too far. Linear rates, you can measure the part and compare it, and you can say, okay, I'm off by 1/1000th per inch, and that'll tell you something. But volumetrically, you can really only see it in a package, in a simulation package like Moldflow. And that's the beauty of it, because it allows you to see where these volumes are shrinking more than others and how that will impact your part. So that's the real beauty of and power of it. But it's really a relative kind of thing. So when you're in Moldflow, every resin might have a different scale of volumetric shrink, but you will see the deltas. And what I found it being useful for, very useful for, is going in and doing our initial studies and then understanding what those fingerprints look like of volumetric shrink, what those gradients look like, and then going back to the customer and say, okay, can we manipulate this by adding ribs or by adding cuts? And that's where I think the real power lies in that particular result.
All right. Next question we have: can warp also be controlled by process?
Yeah, great question. I have done that. The magnitudes of warp control are very low. You can. I did a part here, about a year or two ago, where it was an existing mold, and they had more warp on it was a Delrin part, so it was semi-crystalline resin, and the geometry how it was designed with the same principles we talked about, put a little bit of a warp into a disc. It was basically a cylinder with a disc on it, and the mold's already built. Can't do anything to design at that point. So we were able to go in and play with differential mold temperature. So the idea behind it is you can put more heat to one side than the other, and that more heat will promote more shrink. So you can steer a surface, but the issue is that the magnitudes are very small. So I kind of rely on that as a very fine tuning type approach, but not a primary one. Primary one, you have to go after geometry and correct it up front, and then you have that tool in the toolbox for fine tuning. But great question.
All right, Ray, this next one, they're seeking your comment on it. It's more of a statement. I use the concept of budgeting part tolerances to include variation in shrink, steel tolerances, metrology, capability, etc.
Yeah, I mean, absolutely. I mean, if you think about it, variation in shrink and steel tolerances aren't going to be known until you take those first shots. So what does that mean, though, to you as a customer or you building a mold? What it means is, in order for you to achieve what you're after, you're going to have to go in and tune the steel. So the principal idea always is to tune steel to a final, robust process in a machine. And once you have that, you can start to creep up on that steel to bring these tolerances in. But that comes at a cost. So the fact that you're thinking ahead like that and budgeting it is beautiful, because that's really how it is. It's all, you think about a tool maker and what are they selling? They're selling time and material. It's mainly time. And so that's what we're faced with. So when you use that other technique that I showed you about how to identify those dimensions, you can get an idea how many you have. And and you do have to plan for that and say, okay, if I got 10 criticals and I know I'm going to have to go steel safe, there's going to be added cost to do that. So budgeting for them is a very wise idea.
We appreciate all the questions that are coming in. The next one for you, Ray. What is your workflow for fixing warp in actual parts?
Okay, yeah, great question. So our first stop is Moldflow. So what we'll do is we'll bring a part in. At this point, customers already had a resin picked. Our very first step is gate location. Now, we didn't get into that much today, but gate location can affect part shape. So if we have a critical part as far as shape requirement goes, the first thing we'll do is bring it in and we'll investigate all of the possible locations where we can gate a part. That's where it starts. It's sort of it's a more of a discovery step. And so in that step 2, we'll be able to see how the part warps. We'll be able to see these volumetric shrink gradients and give us that chance to go back with the customer and say, okay, your design and gate approach that we were coming up with, we explore it together and we say, here's your shape, or is this going to be okay with you? And if the answer is no, then we enter the next phase, which is getting in and applying these principles where we're trying to control warp, adding features, taking away mass, and working with the designers to achieve the predicted result. We found that Moldflow has been exceptional at predicting shape. I mean, it's been unbelievable. Magnitudes can be off. If it's saying you get in 5, maybe you get more, maybe you get a little bit less, but directionally, it's been unbelievable, and it's kept us out of a lot of trouble. But certainly, taking it through Moldflow, whoever you work with, I would really suggest that you have them spend time with you in that package or a similar package to unravel these things. You'll be pleased at the results.
Okay, great. We have, I think, what's going to be our final question. Do you work with fiber-filled resins? If yes, how do you warp control? How do the warp control techniques you presented work for that type of resin?
Okay, that's a big question. It deserves a whole nother webinar. But fiber-filled resins are tough. These techniques I talked about, do they play in? And they do, but to a minor degree. I mean, if you just think of glass as a skeleton structure that's inside your part, it becomes very difficult to influence it. Probably the biggest influencer on fiber-filled resins is gate location. And if I had more time, I could show you some parts where you could just take the gate, move it from one area to another and have drastic warp consequences related to it. And it has to do with fiber alignment and manipulation of fiber alignment. It's tough, very tough to do. There's other techniques that we employ too. There's some very good predictive software, like Moldflow will kick out, actual files so we can put compensation in the molds. There's different ways of approaching it, but it's tough. I mean, I always caution engineers that, be sure you want fiber in your part. If you need the stiffness, then you need it. But if you're overkilling it, you might be creating issues for yourself that you don't want to have. But it is tough. Good question.
But he's very good with it.
Yeah, we've had a lot of that. Mm-hmm.
Just reach out to Raydini, he'll fix it.
Exactly.
Unfortunately, that is all the time we have for today's presentation. I'd like to thank our speakers, Beth Harrison-Meyer and Ray Scherer, for their insights. I'd also like to thank our sponsor, Aptex, for its support. Finally, I'd like to thank you, the viewer, for attending this session. I hope you found it to be a valuable experience.